Welcome back. Let's talk about atomic theory, which goes back about 200 years, which is around 1600 or 1700 when people started to become scientifically interested. Okay, but the initial thought about atoms dates back to 440 BC to the Greek philosophers, and it wasn't Aristotle who said that there are four elements: earth, fire, water, wind, and that's just not true. And he got actually in big arguments with the two who came up with the actual atom, the hypothesis of the atom, which is Leucippus and Democritus, who legend has it came up with this theory as they walked down the beach and they saw the sand, and from far away it looked like one big piece of matter. That sand was just one big piece of whatever sand. But as you get closer, as you know, if you look at the individual sand grains, and so they hypothesized that matter is made up of small, hard, indivisible particles called atoms, whereas Aristotle said matter is infinitely divisible, and so they would get into big arguments. But that was not a bad thought, considering how long ago, 2,500 years ago, that's a long time. And then, of course, the Dark Ages, at least in Europe, happened, and no science progress was made. It was simply labeled blasphemous to conduct scientific thought and any kind of logical thought, for that matter. However, it was Gassendi, who was a priest, a philosopher, and a scientist, who in the 1600s made the statement, well, I mean, God created atoms, and that allowed scientists or anybody who was interested in pursuing science and conducting experiments and to do so. And that's really was the major breakthrough, and led eventually to the atomic theory by John Dalton, who in the 1700s took the experiments of Lavoisier and others and put them all together, and he came up with this theory. Atoms are small particles of matter, and if you have a single, and you can break it down, so you can divide it and go down to the smallest particle, and the smallest particle still retains the identity of that particular element, okay, a single atom. But he also said you cannot break it down further, and of course we know that that's not true, but that came later. And then an element is simply a type of matter composed of only one kind of element, like like gold. So if you have a bar of gold, every single atom in this bar of gold is the same. So that's element. And then compound is a combination. We already know this, of two of two or more atoms from the periodic table, and chemical reactions is the rearrangement of atoms in to form new substances, right? So you have to break bonds and make new bonds, and that's a chemical reaction, burning wood, etc. Okay, so we already looked at the law of conservation of mass, which in a way, if you remember back, we took carbon and oxygen and made carbon dioxide, and that was always in the same ratio. So that's in a way the law of definite proportions, right? So when carbon and oxygen combine, they are always combined in the same ratio. But there's also another law called the law of multiple proportions, right? So it can be in a 1-to-2 ratio here, like carbon dioxide, or it can be in a 1-to-1 ratio, right? So that's the law of multiple proportion, and that's true for the nonmetals. The nonmetals, when they combine with other nonmetals, they can form different ratios. So that only applies for those types of compounds. And but it's also true that it's once you have a particular compound like carbon dioxide, carbon and oxygen will always combine in a 1-to-2 ratio. Okay, never in a 1-to-1/2 ratio, and that stays true. And this goes back to what Lavoisier was doing in the laboratory too. He would, and we'll explain how he did this and how we determine these atom ratios when we learn more about the mole and the molecular weights and periodic table. But for now, he took a gram of oxygen and he reacted that with nitrogen, and he found that there are multiple products that are formed that contained a number of nitrogens. And when he cranked out the ratios, that's how he found the law of multiple proportions, or at least that's how he gave Dalton the idea to postulate the law of multiple proportions. Okay, so like nitrogen here is in a 2-to-1 ratio, and 1-to-1 and 1-to-2 ratio. So those were all found, and you should know this already. I mentioned this, that symbols we find on the periodic table are either single letters, and then they're capitalized, like hydrogen, fluorine, oxygen, carbon. Of course, we have more than 24 elements, so we have also either a single letter or two letters, and then the first letter is always capitalized, right? We got to distinguish between hydrogen and helium, and so He is then helium, beryllium, silicon, argon, and so on and so forth. And it's important that you do that you remember that, because there's a difference between CO and CO, right? So this happens to be the symbol for cobalt, and this is carbon monoxide, right? If you capitalize the second letter of cobalt, that indicates no longer cobalt, it's oxygen. So it's important that, and a lot of people will do that when they get sloppy. Like this is sodium, because nitrogen by itself could be N by itself could be nitrogen, potassium, tungsten, silver, and so on. Okay, so the next step was to elucidate the atom, all right? And so here in 1897, so not too long ago, right? About 120 years ago or so, Crookes took this glass tube, and he had an electrode, so you could apply charge here, right? So a cathode and an anode, so positively and negatively charged. He can apply charge there to create electricity flow, but he also evacuated this glass tube, so there was no matter inside of it. And so he would observe a green beam here that would go through, and if you apply the charge to these plates, that beam would actually bend towards the positive charge, implying that the beam itself had a negative charge. And so they would also measure the mass of this particle, this electrically or negatively charged particle, and it had a mass that was less than that of the smallest atom, which was hydrogen. And so that perplexed those scientists, and they had to come up with a new hypothesis and then conduct more experiments to find out more about these atoms. Is that really the smallest part, or are there subatomic particles? And so this guy, this American scientist Robert Millikan, 110 years ago conducted the experiment that would determine the mass of an electron. And he had this chamber here and a little looking glass on the side, so he could observe these particles, and he would spray really small, finely dispersed oil particles and then apply charge to these plates. And as these oil droplets fall through, they would pick up electrons from this charged plate, either one or two, and then he would measure the size and the diameter and the rate at which they fall. And based on that pretty simple experiment, you have to remember that there was no real sophisticated instrumentation. There were no electron scanning microscopes or things like that, so they had to work with what they had, and this was pretty clever. And so they actually determined the mass of an electron versus the mass of an electron, which was 1,700 times smaller than that of the smallest atom, hydrogen. So not smaller, but had a mass that was less than that. Okay, so they knew if they had a negative particle, they had to have positive particles, and so they came up with this plum pudding model. The plum pudding is similar to a chocolate, let's call it a chocolate chip muffin, right? And so they thought that this was a positive blob. Okay, so you had some sort of positively charged blob, and within it you had these chocolate chips, these electrons here thought because they were smaller, they thought they weren't. They are actually not smaller; they're larger, but they didn't know that. They just know they had less mass. So that's the theory that they came up with, and that went well for a little while until Ernst Rutherford came up with this cool experiment. He took a gold foil and he rolled it super thin, where he would just have 3 or 4 layers of gold atoms. So, but it wasn't, and then he shot alpha particles, which is a form of radiation, through this gold foil. And what he found is that 97% of these alpha particles, they would go straight through the gold foil, so through the atoms. And some of them would reflect, as you can see here, and go to the side, and others would just not go through in a straight line. So, but it was only 3% of that. And so in order to understand that, you have to understand that an alpha particle is a helium particle, here shown on the right, that has been stripped of its electrons, right? So no, they did not know, they just knew that this was a very fine, small particle, but I might as well tell you here, right? So you have, in the center, you have what's shown here, this little cluster that's called the nucleus, and it has protons and neutrons in it, okay? And then you have these green particles here, and they're electrons, and they're mobile, they just go around, right? And so they actually take up all of the space here. And that's exactly what we see here. These gold particles are made up the same way. But this helium particle and so helium has 2 protons, and protons are positively charged, right? And so it has to have 2 electrons to be neutral. So if you make a helium plus 2 particle, you no longer have this cloud, right? So if you bombard this under any matter, it's going to go straight through. This is why alpha radiation is not exactly healthy for the human body, or any kind of radiation. So, but this would explain how these helium particles, they are smaller than any atom. They can go straight through these electron clouds, and that's what you see here. You see these beams, these alpha particles go through. And so they had to revise their theory, and they came up with that, what I was just telling you. The nucleus is in the center. You've got a positively charged clustered, and then you have electrons on the outside that are going around. So they did away with plum pudding model, and so they had to further pursue. Then they found the proton in this case, right? So there's a positively charged particle, which is has a mass that's 1,800 times that of an electron. Okay, and so now the neutron wasn't found until 1932. That was the toughest one, and so there's a summary of the subatomic particles. He listed here. So the mass of protons and neutrons is roughly the same, and AMU stands for atomic mass units, which is of course like a really small number, these tiny little particles. Because an actual mass in grams here, a proton is 1.67 blah 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 times 10 to the minus 27. That's very tiny. And the mass of an electron here is, of course, as I said, much smaller. That was found by Chadwick there in Mulliken. But also what needs to be noted here is the charge, that a proton has a positive charge, an electron has a negative charge, and neutrons, which are also part of the nucleus, they hold that those protons together in the center have no charge. They are neutral, therefore the name neutron. And so just to illustrate how small these particles are, one illustration is, of course, the baseball field that I always use. If you have a baseball field, and I understand that a baseball field is not circular, but if we took an atom, a single atom, and we blew it up to the size of a baseball field, right, we would have a nucleus, and that's in the center of the baseball field. And that nucleus is the size of a fly. And the rest, the entire baseball field, this is where the electrons are, right? So that's how much space an electron takes up. Well, But you got to also remember that this electron goes around in 3 dimensions and fills up the sphere. So you get this ball-like spherical atom. Okay, so back to this question here. 1 cup of water. Let's say if I had a cup of water, 12 ounces, and I calculated that myself. I know that 1 water molecule has 2 hydrogen atoms and 1 oxygen atom, and I also can calculate how many molecules are in 12 ounces. And so I don't want to do this calculation. I just want to tell you that happens to be in 1 cup of water. That happens to be 3.5 times 10 to the 25 atoms. And just to put that into perspective for you here, this is how many zeros we have. We have 25 zeros. So here's 1,000. There's 1,000,000. Here's 1,000,000,000. And here's 1,000,000,000,000. So 1,000,000,000,000 is just 1 times 10 to the 12, right? But that's 10 to the 25. So this is actually 1,000,000,000,000 times 1,000,000,000,000 times 35. That's how many atoms, oxygen and hydrogen together, are in 12 ounces of water. So that's a lot, and so that should tell you how small these atoms are. Okay, shifting gears just a little bit, and then I'm gonna quit before I get into the periodic table too deep. The person who put all this together, the periodic table, or started to figure out that there are trends and groups and similar behaviors between, like gold and silver are very similar, and sodium is highly reactive, and so is potassium, so they belong in the same category. And why that is, and that it's Dmitry Mendeleev who started arranging the elements and found trends by atomic weights and similar properties here. And so he grouped them all together now. And so this is not what it looked like, but this is what our modern periodic table looks like. So we have these groups here, right? So those columns are groups. Here's lithium and sodium and potassium and rubidium, and they all are highly reactive, and they all have a lot in common. And then you have these noble gases here in the last column, and they're very unreactive. They're the complete opposite. And so there's a lot to be said here, but Mendeleev also found gaps in the periodic table. Now, for example, they found a bunch of elements, but not all of them. And so one element that was missing that hadn't been discovered was germanium. And so he predicted that there has got to be an element that fits between silicon and tin based on the molecular weights and the arrangement of the periodic table. So then he predicted that, and later on they discovered germanium, which is a really rare metalloid. Okay, and so I'm going to stop here and then talk about the periodic table in more detail in lecture 3.